So welcome to this jumbo session. So we have 6 10-minute talks. And the talks are not all about one topic, but they're really all of them can be related one way or another to one of 2 topics. So they're either about high-dimensional geometry and linear algebra and metric embeddings in some way, or somehow related to bipartite matching. So let me tell you about these 2 clusters of talks one after another. So the first talk is by Perez, Singh, and Bishnoi. So this is a result. There are many ways to introduce it. One is it's a result about randomized rounding. So in randomized rounding, you have a polytope and you have a point inside that polytope, and you want to round that point to a vertex while preserving some, functional or something like that. And so this is very easy if your polytope is a cube. You just round each coordinate independently. But if it's something more complicated, like the convex hull of spanning trees of a graph. So this is something that came up in studying the traveling salesman problem. Then it's not so clear what you should do. So what they prove is this very general result, that if you have a convex hull of bases of any matroid, then it's possible to do this rounding in a way that gives you a distribution which is not independent but almost as good. It has this thing called the negative association property, and all your concentration bounds and things continue to work. And the very nice thing about their proof is that there's a nice connection. It uses this idea from the paper of Lovin and Meka in discrepancy theory based on random walks. So that's the first paper. Then we have a paper about distance oracles by Dinitz and Zhang. And what's a distance oracle? So it's a data structure. So given a metric space, you want a data structure with the property that you can query the distance between any 2 points quickly, and you want this data structure to be small. And so there are some general theorems that show that such things exist for all metric spaces with some bounds. And what they initiate in this paper is an instance-wise study of this problem. So they ask the more refined question: if I give you a metric, can I find in some sense the best data structure for that metric? And what they prove is that you can, and the key insight in their work, and the new idea is that in all these constructions, you use randomization to construct some sort of net of the metric space. And what they realize is that you can actually somehow optimize over that net using convex optimization. And they prove some approximation bounds and hardness for this problem. Then there are 2 papers on locality-sensitive hashing. So this is some device that's used in very applied work and in very theoretical work. And what it is it's a way of hashing points in a metric space with the property that points that are close are likely to be hashed into the same bucket, and points that are far are not. And so the first paper, which is by Kennedy and Ward, studies a case where the metric is just a Euclidean metric on the sphere. So this is a setting that comes up a lot. And the status of this problem, before this work, was something like: there's a very simple algorithm called cross-polytope hashing, which seems to perform well in practice, but people couldn't prove that it has the optimal bounds. And then there were some much more complicated algorithms which people could prove optimal bounds for, but they were, it wasn't clear how they did in practice. So this work bridges this gap. It shows that actually this simple scheme also achieves optimal bounds, and it has a very clean sort of like 1 or 2 page proof of this fact. Then there's another paper on locality-sensitive hashing. This is the paper of, so it's a paper by Cercetti, Kumar, Pancanesi, and Tiroli. And it addresses the following question. So for locality-sensitive hashing, what was previously known is that, you can do it for some metric spaces, and you can't do it for other metric spaces. Or actually, the notion they use is the notion of a similarity measure. But and that was sort of what was understood, that sometimes you can do it and sometimes you can't. So they asked the more refined question, given a similarity measure, is it close to one for which you can do locality-sensitive hashing? And they come up with a definition of this, which they prove that many similarity measures that are used in practice for which you couldn't do this before, they prove that these are close to ones for which you can do locality sensitive matching. And so they thereby extend this range of similarity measures for which you can do this. Okay, so that's the first cluster of papers, and then there are two papers that are somehow related to bipartite matching. So one of them is related to online bipartite matching. And in this problem, there's a bipartite graph, and you're given the vertices one by one, and you have to choose choose matching edges online. And you want to do some competitive analysis to say that, well, even if you do this online, you do almost as well as what you could do offline. And what they do in this paper is they consider, so typically what we like to do is bound the congestion in online bipartite matching, which is just the maximum load on any vertex. So what they do is they consider this much stronger objective that instead of maximizing the L infinity norm of the loads, you want to minimize the L infinity norm, you want to minimize the LP norm for all P simultaneously. Which sounds like a much harder goal, and it is. And they show that you can do this. They show that you can do this online if you're allowed to undo a certain bounded number. And then the last paper. Okay, so the last paper is about bounding non-commutative rank, and that might sound kind of scary, but you can think of it as a somehow generalization of Hall's theorem. So everybody knows Hall's theorem, which says that a bipartite graph has a perfect matching if it doesn't have a shrunk subset. If it doesn't have a shrunk subset. And what they do is that they study a sort of linear algebra generalization of this problem. And in this problem, the graph is replaced by a subspace of matrices. And the question analogous to finding a shrunk subset is, do all these matrices have the property that there's some subspace that they all map into a smaller subspace? And so that's some sort of generalization of a Hall set. And there was this, this problem comes up in a bunch of different contexts. There was this work of Garg et al. Last year where they showed how to solve this for vector spaces over the rationals using a randomized algorithm. And this work gives a deterministic algorithm over any field with connections to many other new connections to different areas of math. So, okay, so with that, Yuval is our